So welcome everybody to the third day of our meeting on neutron stars as multi-messenger laboratories for dense matter. We already had two very exciting days on neutron star simulations and observations and what we can learn from them. And today we have another great day on nuclear physics with 5 excellent speakers. I wanted to say to the speakers, you have 20-minute slots. I will give you a warning after 15 minutes and after 20 minutes when you really have to wrap up. And for the audience, if you have questions, you can either put them into the chat or you raise your hand after the talks. And then we have another discussion session at the end of the after the 5 talks where we can discuss other questions that you have. And I wanted to say, if you want to ask a question anonymously, you can send it in the chat directly to me and then I will ask it on your behalf if you indicate so. Okay, so we can begin with our first talk. Chuck, could you please share your screen?
Great.
Okay, so first speaker is Chuck Horowitz from Indiana University, and he will tell us about the P-REX 2 experiment and neutron-rich matter in the laboratory. Thanks.
So hello, thanks for the chance to talk. Good after Zoom, I guess. Want to talk about the P-REX 2 experiment. We're studying neutron-rich matter. If you compress anything enough, electrons capture on protons to make neutron-rich matter. The material is the heart of many fundamental questions in nuclear physics and astrophysics. What are the high-density phases of QCD? Where did the chemical elements come from? And what's the structure of many compact and energetic objects in the heavens? What determines their electromagnetic, neutrino, and gravitational wave radiations? So today, I want to focus on neutron-rich matter in the laboratory. If you consider a heavy nucleus such as lead-208, we expect lead to have a neutron-rich skin. If we can focus very accurately on this skin region where it's neutron-rich, then we can study a little bit of neutron-rich matter in the lab. So this is a simple relativistic mean field model for the densities in lead. The dashed red line is the proton density. So there's 82 protons, the density versus radius. The black dashed is the neutron density, so the 126 neutrons. And the P-REX experiment is focusing on how much the neutrons are expected to stick out compared to the protons. We're measuring the thickness of this neutron-rich skin. And the way we do it is to use parity violation. So in the standard model, the Z boson couples to the weak charge. The weak charge of a proton is small. 1 minus 4 sine squared theta to tree level in the standard model. And the weak charge of the neutron is big. So the weak interactions at low momentum transfer provide a clean electroweak probe of the neutrons. What's measured is the parity violating asymmetry. This is the fractional difference in cross-section for scattering left-handed electrons or right-handed electrons. The asymmetry arises from the interference of photon and Z0 exchanges. So it's order G Fermi Q squared, and then it's a chance to measure the weak form factor. So FW is the Fourier transform of the weak charge density, which is essentially the neutron density. So we have a model independent way, in principle, to map out the weak charge density of heavy nucleus. And the important point is this electroweak reaction is free from most strong interaction uncertainties. So the theoretical interpretation of the experiment is very clean. So the experiment runs in Hall A at Jefferson Laboratory in Virginia in the US. 1 GeV electrons are scattered at about 5 degrees. And the measured parity violating asymmetry is around 550 parts per billion, so half a part per million. So in the plot, what's shown on the x-axis is the parity violating asymmetry, and the green band is the total experimental error. I'll come back to that next slide. If we look at a correlation, there's lots of density functional models are plotted as points. So in a model, you can, of course, calculate the electron scattering and the parity violating asymmetry. And then you can also calculate the root mean square radius of the weak charge distribution, so what we call the weak radius. And so that's plotted on the left-hand y-axis. And there's a very strong correlation between the parity violating asymmetry and the weak radius. And so we can use that correlation to extract the weak radius. So that's the distribution of weak charges, which is mostly the distribution of neutrons. And so we can also get the neutron radius, or in particular, the neutron radius minus the proton radius, which we call the neutron skin. And so that's plotted on the right-hand y-axis. The thickness of this correlation is indicated by the red dashed lines. It's not a perfect correlation, but it's very good. That thickness comes from some very small uncertainties in the surface thickness of the weak charge distribution. So I'll talk about that thickness of the correlation in just a second. This model dependence is much less than the experimental error. Okay, and this procedure allows us to extract the weak radius of lead-208. It's 5.800 Fermis, and that's significantly larger than the well-known charge radius of lead, which is 5.50 Fermis. So that difference is the weak skin, so the weak charges stick out a little bit compared to the electromagnetic charges, or equivalently the neutron skin, the neutron radius minus the proton radius, is 0.283 plus or minus 0.071 Fermis. So just a word, let me try and give you a little bit of a feeling of the P-Rex errors. So these nuclear physics, there's the measured parity violating asymmetry. There's a statistical error of about 16 parts per billion, a systematic error of 8 parts per billion. So bear with me just a second. Let me talk a little bit about the systematics. Many of the systematic errors come from helicity correlated beam properties. So when you flip the spin of the electrons, any change in beam properties, such as the position of the beam, the average energy, the intensity of the beam, if anything depends even slightly on the spin of the electron, then that can introduce a systematic error. And so these helicity correlated beam properties are measured constantly during the experiment. And when necessary, there's feedback controls in place to keep the helicity correlated beam properties small. There's a lot of experience from many previous parity experiments, and the very high quality of the electron beam at Jefferson Lab from the superconducting accelerator. The beam is very quiet, very stable, And that helps with these systematic errors. And let me mention one person in particular. Paul Sauter basically has spent his whole career over several decades controlling and reducing systematic errors in parity experiments. So the small systematic error of the P-Rex 2 experiment is a systematic, remarkable achievement that represents a lot of hard work by a lot of people over a long time. And then finally, let me mention this small model error. Undoubtedly, this model error is the error that's most often confused or misunderstood. To determine the weak, determine an RMS radius, it's the derivative of a form factor in principle at 0 q squared. You can't measure at 0 q squared, you measure at a finite but small q squared. And therefore, we need to make very modest assumptions about the surface thickness of lead. And these assumptions about the surface thickness lead to this small model error, something like plus or minus 0.013 Fermis, which is small compared to the total error, which is dominated by experiment, dominated by the sum of the statistical and systematic errors. Should there be any question about this model error, one can always directly use the measured weak form factor. So it's the Fourier transform of the neutron, the at the small momentum transfer of the experiment. The value is 0.368 plus or minus 0.013. And again, that error is the sum of statistical and systematic. And this form factor doesn't have any assumptions about the surface thickness. Okay, and again, wanted to emphasize this is an electroweak reaction. The further theoretical errors from uncertainties in radiative corrections are very small. Great. So we want to compare the results for lead to neutron stars. A neutron star is 18 orders of magnitude larger than lead, but it's the same neutrons, the same strong interactions, and the same equation of state pressure as a function of density. The pressure of neutron-rich matter pushes the 44 extra neutrons out against surface tension. And so the higher the pressure, the thicker the neutron-rich skin. So Rn minus Rp in lead is strongly correlated with the pressure of neutron-rich matter near nuclear density. If you like, pressure is force per unit area. To measure a force, you use a spring. In this case, it's the known surface tension of nuclei. You measure a force with a spring and a ruler, how much the spring is stretched, and P-Rex is that ruler. So we talk about the radius, neutron radius in lead, that's what P-Rex measures. The radius of a neutron star also depends on the pressure at nuclear density and above. So the measurement of the radius of lead in the laboratory constrains the pressure and has important implications for the structure of neutron stars. So let me collect a bunch of results from Monday and Tuesday of this workshop. So on the y-axis here is the deformability, and this is the deformability of just a 1.4 solar mass neutron star. So this, of course, is related to the deformability measured by LIGO and Virgo from GW 1708-17. On the lower x-axis is the radius of a 1.4 kilometer, excuse me, a 1.4 solar mass neutron star. And so we heard a lot of nice talks, nicer and other X-ray observations constraining this radius yesterday. And then finally, the upper x-axis, we plot the neutron skin thickness in lead, again, the neutron radius minus the proton radius of lead. And so to tie these three observables together, we've done a series we use a series of relativistic density functionals. They're indicated by these blue dots. Each density functional has a different density dependence of the symmetry energy. More on that in just a second. Given a density functional, we can calculate the structure of lead in the neutron skin. Given the functional, we have the equation of state, and so we can calculate the radius and deformability of a neutron star. So each functional allows us to calculate all three quantities. As we heard, the gravitational wave observations place an upper bound on the deformability. And so this dash yellow line at the bottom of the figure, or near the bottom of the figure, is perhaps the most aggressive upper bound. So this upper bound assumes the deformability of the two stars are based on the same equation of state, and it has some model dependence. Basically, it assumes a form for the equation of state, fits it to the GW 1708-17 data, and then plots or allows you to determine the deformability of a 1.4 solar mass neutron star, even if the neutron stars in the merger were not exactly 1.4 solar masses. So that's some of the what went into the dashed yellow line.
Chuck, you're at minute 15.
Great. So the favored deformability area is near the bottom of the plot. And if you look at the blue dots, as we've heard before, this suggests a relatively small radius of about 13 kilometers or less. We can add to this figure nicer results, and I just plot one of the two groups for simplicity. This is for J0030. So this is the pulsar near 1.4 solar masses. And then finally, here's the P-Rex2 result for the skin of lead. There's considerable overlap between P-Rex and nicer. P-Rex favors the stiffest equation of state, the highest pressure, but there's considerable overlap, and of course the error bar is significant for P-Rex. And so what you're testing by comparing these is the density dependence of the equation of state. P-Rex favors, or is the observable that involves the pressure at the lowest densities, nuclear density and below. There's slight tension between P-Rex2 and LIGO, but there still is a small overlap region. Great. So just a couple words on the symmetry energy. The symmetry energy describes the increase in energy of nuclear matter as one goes away from equal numbers of neutrons and protons. If the symmetry energy has a large density dependence, it increases rapidly with density, then it will tend to push the 44 extra neutrons out of the high density interior of lead, where the symmetry energy is very big. It pushes it out into the low density surface region. So a large density dependence of the symmetry energy leads to a thick skin. And indeed, using this correlation, the density dependence of the symmetry energy, this parameter L, is predicted to be relatively large, 110 MeV. But again, the experimental error is big, plus or minus 36 MeV. Great. So in my last couple minutes, I wanted to mention we've made one more measurement. This is the C-REX experiment. It's a similar measurement for the neutron radius in calcium-48. Chiral effective field theory expands the 2-nucleon, 3-nucleon, and principal 4 or more nucleon interactions in powers of a momentum transfer over a chiral scale. There are important 3-neutron forces, which are hard to directly observe in few nucleon scattering. These 3-neutron forces increase the pressure of neutron matter significantly. They also increase the neutron skin thickness of both lead-208 and calcium-48. The only stable neutron-rich doubly closed shell nuclei in nature are calcium-48, 28 neutrons and 20 protons, and lead-208. The P-REX measurement on lead is better for inferring the pressure of uniform neutron matter and the structure of neutron stars. The C-REX experiment on the smaller calcium-48 allows more direct comparisons to chiral effective field theory. One can perform microscopic calculations for the lighter system, which have not yet been done for lead-208. Data taking for C-REX has been completed. The analysis is underway. So let me close by showing you a plot. This is the neutron skin of lead on the x-axis with the P-REX2 result. Again, neutron radius minus proton radius for lead-208. The y-axis is the neutron skin in calcium-48. Let me mention one microscopic chiral effective field theory calculation. This is the band at the bottom by Hagen et al. This is a coupled cluster calculation, and it predicts a very small neutron skin for calcium-48. And they claim the complete error bar is the brown region as shown. The thick neutron skin in lead, along with the simple expectation that a thick skin in lead tends to be correlated with the thick skin in calcium, suggests that this chiral effective field theory calculation for calcium-48 may be wrong, but let's wait and see what C-REX gives. So I thank you very much for your attention, and let me emphasize a really good graduate student who's been helping me in this, so Brendan Reed, and I thank you again. Happy to answer questions.
Thank you very much, Chuck, for this great talk. Are there any questions? If you have questions, please raise your hand in Zoom or write it in the chat. And I see that Prakash asked something. Do you want to ask him, Prakash?
You go ahead.
Okay, so Prakash asked in the chat, I think it's back to the slide where you compare the different correlations.
Different here?
This one, yes. And for the P-REX result, so if you exactly, why isn't it centered at 0.283 Fermi at the top scale?
Yeah, so I apologize. This may be a slightly earlier version of the talk. And to avoid some confusion, there's two slightly different results we have for the neutron skin. One is the result of just P-REX2 itself, and that's may be what I plotted on the slide. We also combine it with the original P-REX1 result, which is a slightly bigger skin, although P-REX1 has a significantly larger statistical uncertainty, so it doesn't change the result very much. So I think the answer to your question, Prakash, is this is just the P-REX2 result rather than the sum of the two, which would give a slightly different, slightly larger number.
So the very last slide, the penultimate slide, it is centered at 0.283, I believe. Yes, that's why I was confused. So this is your combining 1 and 2, is that correct?
Yes.
And that's the larger one, but if you just have P-REX2 itself, then it will be smaller.
Yes. So P-REX1 has about 10% of the statistics of P-REX2. And so the experimental collaboration went ahead and combined the two, since they're consistent, in order to get a slightly smaller total error.
But is that the only compelling reason? Why not believe P-REX2 altogether?
Yes, and you certainly can. They're completely consistent, given the error bars. In fact, there's essentially no real difference.
Thanks.
Are there any other questions? Otherwise, I have one. So P-REX is not the only experiment that measures the neutron skin of lead, or claims to have measured the neutron skin of lead. There are also other experiments using dipole polarizability that find something, I think, around 0.16 plus minus 0.03, 0.04. Could you comment on this, please?
Yeah, so careful with how you phrased your question. So the dipole polarizability is a very interesting measurement. It's a very useful measurement, but it's not the neutron skin. So the inferred value is somewhat model dependent, the inferred value for a neutron skin. So you should just use the dipole polarizability itself. If you looked at the dipole polarizability, for example, it tends to favor a smaller symmetry energy than, or smaller density dependence, a smaller L than the P-REX value. But because, unfortunately, of the P-REX relatively large error, they're consistent.
Okay.
May I ask?
Yeah, go ahead, please.
May I ask? Hello?
Yeah, please go ahead.
Yeah, thank you. I have very simple questions. Have you any results on the dependence of the strong interaction on the distance between nucleons?
So let me try and understand your question. What we're measuring is the weak charge distribution in lead-208. That's the experimental observable. In various models, this density can depend on short-range correlations. I would say that's a theory issue. How you interpret our measurement of the weak skin in your microscopic model with nucleon-nucleon correlations, that's up to you.
Yeah.
And so I look forward to more microscopic calculations.
Have you analytical formula for description this dependence?
No.
No. Thank you.
Okay, I see that there are more questions in the text, but maybe we can move them to the discussion session in the end, where I think we should definitely come back to PREX. So I want to thank Chuck again for now, and let's continue with our next speaker. Okay, Andrew, can you share your slides, please? Great. Okay, so our next speaker is Andrew Steiner from the University of Tennessee, Knoxville, and he will tell us about combining electromagnetic and gravitational wave observations to determine the nature of dense matter. Please take it away.
Okay, can everybody hear me?
Yes.
Okay, thank you very much. So I want to thank you very much to the organizers for the opportunity to speak briefly. I also want to acknowledge my excellent collaborators for the particular work that I'm going to talk about today, most of which is based on a paper by my graduate student, Mohammed Al-Mamoun, who just goes by Mamoun. But also there's work from previous graduate student Spencer Bloin, my previous postdoc Sophia Hahn, and then of course several other collaborators around the world, whose efforts I very much appreciate. So in any case, I'm going to get straight in. Oh, sorry. So I want to talk a little bit about because a lot of us are talking about statistics in the context of Bayesian inference, prior distributions, and the space of all possible equations of state. So the space of all possible equations of state is simply if you think about the space of all possible pressure and energy density functions, which are hydrodynamically stable and causal, this space is uncountably infinite, and that means in certain particular things about what we do with our priors. And in particular, this means there's no way, unambiguous procedure of listing or plotting or analyzing equations of state. And this means essentially there's no such thing as a model dependent or model independent analysis. The space is just too big. So whatever you do, you must put some sort of prior distribution. Also for this reason, there are some things that you cannot say. You cannot say most equations of state do not have a phase transition. Well, you can say that, but you can only make probabilistic statements like that with respect to some prior distribution. And here I sometimes use the word prior distribution sort of generically to refer to the various model assumptions that we put in, the sort of whatever the special sauce we put into our particular analysis. Because this space is so large, you must have a prior distribution, and it's just a matter of talking about what that prior distribution is and understanding what the impact on the results. And because this comes up later, I thought it was worth talking about it a little bit today. In particular, we're still in a data-starved regime. Okay, if LIGO had 100 neutron star mergers, then maybe we'd be in a different story. Maybe eventually LIGO will put me out of a job, but in the meantime, we have a limited number of data which don't always tell us a consistent story, so we have to figure out some way to proceed. And one way to do this is to use a prior distribution. There's no optimal way of doing this, okay? And you can see this. Every theorist has their own particular favorite way of looking at the data, and they have their own sort of prior beliefs. Really, the thing that always wins is better data sets. Okay, I'm always excited about more data. So in any case, with that particular introductory material, I wanted to talk about what the goals of the combined analysis that Mamoun and our collaboration did, and then also what the goals of this talk. So we wanted to see what information can be attained on neutron star mass and radius curves, and also the equation of state with as big of a data set as we could. It was reasonable. Quiescent low mass X-ray binaries, photospheric radius expansion X-ray bursts, NICER, and these are all electromagnetic constraints on neutron star structure, and then gravitational waves. We've heard a little bit about NICER. I'm not going to talk too much in detail about the quiescent low mass X-ray binaries and photospheric radius expansion burst, the individual details of how we how the community obtains mass and radius constraints from these particular objects. But then again, if you have questions about that, of course, I'm happy to discuss that later. Of course, we want to anchor our particular equation of state model in up-to-date nuclear physics. And what does this mean? This means that for neutron matter, we use a combination of nucleon-nucleon interaction based on chiral effective theory, plus many-body perturbation theory to get the equation of state. And actually, we don't do the equation of state calculations ourselves, or at least Mamoun and I do not do those. We use a posterior distribution, which is kindly given to us by Ingo. And then we combine that for nuclear matter, for isospin symmetric matter with equal numbers of neutrons and protons. Laboratory nuclei are really the best way of understanding that. So we use posterior distributions, which were generated from previous Bayesian inference from nuclear structure data, principally binding energies and charge radii. Then, as I mentioned in the first slide, prior assumptions are important. And so we want to take care to try to show how our results might depend on our prior assumptions. Okay? And one of the important, it's been sort of long understood that the priors at high density are particularly important. And so there are a bunch of different ways of parameterizing or expressing the equation of state space, basically of organizing this uncountably infinite space of all possible functions that are causal hydrodynamically stable. Polytropes have a long and storied history, and so we use those. There's nothing in principle that rules those out, but then these are just line segments in the log space, and we also choose line segments in the linear space, in the pressure energy density space, just because this turns out, and we've known this for a while, that these two turn out to be options which show interesting differences, but would otherwise be perfectly physically reasonable. And then we want to also attempt to determine if the electromagnetic observations contain some sort of systematic uncertainties which are unaccounted for. And the way we do this is by simply asking the question, well, look, we have the electromagnetic, let's do some multi-messenger astronomy, let's compare this with the gravitational wave observations and see if those agree. So here are results for the mass radius curve. I'm just going to jump right in. The vertical axis, is of course mass, but it also shows different data sets. And the two columns represent the two different priors at high density, polytropes on the left versus line segments on the right, 3p or 4l. And you see that, for example, for the radius of a 1.4 solar mass neutron star, it doesn't matter so much that maybe only at the high density limit, but you still get approximately the same 2 sigma, or as these are actually, these are actually 95% credible intervals, but the limits on the radius of a 1.4 solar mass neutron star. A little bit of variation at the high large radius end. The results for lower masses are more prior dependent. So now there's a 0.3 third of a kilometer variation at the low radius end too. And I wanted to point out that I would send a message to the universe because I would really appreciate a very loud signal to noise of 2 1 solar mass neutron stars. That would make everything really nice and pretty for us. So please, universe, do that. The results for higher masses, for example, a 2.4 solar mass neutron star, they're sometimes hidden up here, but they're there. They appear less prior dependent, but this is actually a little bit deceptive because the number of equations of state which actually get up there is somewhat quite small. What you actually might look at for higher masses is the maximum mass posterior distribution, which varies quite significantly. So there's still some prior dependence up at large masses. And of course, this is why the nicer results on J0740 are so important and exciting. I wanted to look at, we wanted to look at systematics a little bit. The way we do this is not the optimal way. This is just a way, and this is the first way we chose. We just do a Gaussian blurring. Every time we have a probability distribution in the mass radius plane, we fold it with some uncertainty. We assume these are proportional in order to make the parameter space small. And the difference, so that's the difference between these two panels, the 5th and 6th panel here in this figure, and the 7th and 8th. And you see that there's basically no difference, okay? So it appears not to make a significant shift in the mass radius curves, okay? This does not prove that there's no systematic uncertainty, by no means. What this method does is it fails to prove that the EM and GW data are inconsistent, okay? So maybe if we tried harder, we could not fail, we could prove that they're inconsistent, but we have not yet succeeded, okay? Also, unrelated aside, that it turns out for this particular analysis, in large part because we're including all of this information from the quiescent Lomas X-ray binaries and the photospheric radius expansion X-ray burst, NICER's result from J0030 makes only a small change, and that's the difference between the 3rd and 4th panels and the 5th and 6th panels, okay? So it's interesting to look at the equation of state results because those are qualitatively different from the mass radius curve results. We find, for example, basically sort of a 50% uncertainty in the equation of state posteriors just because of the prior assumptions, okay? So you can get different equation of state posteriors depending on what sort of secret sauce you're putting into you're doing your calculation on the equation of state. The origin of this is partially that, for example, phase transitions give the ability to, increase the pressure at one density and decrease it in another and sort of make up for it. So different ways of rearranging matter inside the neutron star in subtle ways. I just wanted to explain the plot that there's no relation between the radius of a 1.4 solar mass neutron star and the maximum mass. And so this is important because maximum mass is an important quantity for understanding the fate of a neutron star merger, but it's very difficult to extract that information just from radius data alone. Okay, there's other ways to do this. So I wanted to talk, of course, we did this analysis and we finished it last year, and then everything went crazy, and the past couple months have sort of upturned everything that we thought we knew. Okay, so what about PREX2 and NICER J0740? Chuck gave a very excellent explanation of this result, and because my particular niche is combining these electromagnetic and gravitational wave observations, I wanted to point out that there's likely some tension between, of course, you see the tension, a little bit of tension here between sort of G and H, our sort of nuclear theory results on S and L, J and L. And so these small values of L tend to suggest smaller neutron star radii. Quiescent low mass X-ray binary observations, in particular the neutron star in NGC 6397, also suggests relatively small neutron star radii. On the other hand, it's obvious that the PREX2 result and the NICER result on J0740, which we heard about yesterday, I believe, those suggest large radii. So what do we do with this? Well, there are a couple of things. I just want to enumerate the possibilities which I had in my head. Well, of course, there could be systematics lurking in the quiescent low mass X-ray binary or the NICER observations. I'm not going to tell you anything about the probability of there being systematics. I mean, this is just, in particular, it's very easy to think, oh, well, the quiescent low mass X-ray binaries have a low radius because they're not actually observing the entire neutron star surface. And what's actually happening is they're a hotspot. And so that means a larger neutron star radius. And we've looked at that possibility before, not in this particular paper with Mamoun, but it's perfectly reasonable. You have to be careful because you can't do it to all the neutron stars. You have to do it to some and not others, et cetera, et cetera. But nevertheless, like there could be systematics there. Of course, there could be some theoretical systematic, which I'm not going to speculate on, which moves this up, whatever this is possible. I don't believe anybody. I believe everybody, one of the two. Of course, there could be some, Chuck mentioned this correlation between the form factor at this one value of Q squared and some L. Maybe there's some reason for a failure of a correlation there. Again, I don't have any reason necessarily to suspect that, but this could be. What's going on? Or look, or they're all right. These aren't 5 sigma results, right? These are sort of 1 sigma results, right? To 2 sigma, these all agree anyway. As Chuck sort of pointed out with his overlap figures, everything does overlap at some point. So maybe we're just a little bit unlucky for some reason, and what appears to be a disagreement is actually an agreement, and everything's fine. I don't know. The best way to resolve this is, of course, more data. And I think it would be nice to put more NICERs on the ISS. And I would like to do PREX another 500 times. But, we'll see what we have money for.
Andrew, you're at the 15-minute mark.
OK, great. So for the last couple minutes here, and hopefully I'll be finished early so we can talk. I wanted to go beyond the equation of state. It's nice to talk about the pressure energy density relation, but there's a whole ensemble of nuclear physics and properties and about the interaction between neutrons and protons, and then obviously the prospect of exotic matter inside a neutron star, which we would like to understand. Okay, even if we get our 100 neutron star mergers from LIGO, it doesn't mean we'll be done, which is good because I still want to work in this profession for a little while. And so one way of doing this is attacking a different data set, this thermal emission from isolated neutron stars. And so here you see the data is sort of in boxes, and the theoretical curves are given in these uncertainty bands. The idea is just that by and large, a neutron star is isothermal, and so you just watch it cool over time. And the cooling is just related to the photon and neutrino luminosities. So if you know the equation of state, you can compute these neutrino luminosities and photon luminosities, and then do a simple stellar evolution calculation and determine these curves. So what we have done is what I refer to as the first large-scale Bayesian inference for neutron star data. We actually do a Hartree calculation of the nuclear structure in anticipation of eventually constraining our data with PREX. For now, we just use the charge radius and binding energy of lead-208 and I think another nucleus. We, of course, include the radius information. We didn't include LIGO in this particular analysis because it took a while, but eventually we'll put that there too. This is just the one neutron star in the M13 globular cluster. And of course, we also include the neutron star cooling data for every slide. In order to, because we have the equation of state, the composition, and all of these astronomical data, it needs a relatively large parameter space. We have 70-dimensional parameter space. So, and at each point, in principle, if you wanted to do the full problem at each point in this 70-dimensional parameter space, you'd have to do a nuclear structure calculation, the solution to the TOV equations, and then solve the stellar evolution equation several times to do neutron star cooling. Obviously, we have a simplified way of approaching that with a Gaussian emulator in any case. What are the results? The cool thing about doing this is now we have information on the composition of the neutron star and not just the equation of state. Okay, so this is the proton fraction on the x-axis, the sort of probability on the y-axis. There are some complications with the Vela pulsar, which we can talk about later, but they don't make a a big difference for the particular thing that I'm going to talk about today, is just this proton fraction. And you see the pink here, the red or pink is for a 2 solar mass star. The blue is for a 1.4 solar mass neutron star. And so you see for large masses, the proton fraction is larger than this vertical bar. And what that means is this implies a direct ERCA process, basically just neutron beta decay, which very efficiently cools neutron stars. It cools the entire star quickly. This is fine because much of the data is at large luminosities, not at small luminosities. So we have to presume that most of these stars then have small mass, not a large mass. But then again, this is a little strange. We have to maybe these isolated neutron stars tend to be less massive, because of evolutionary reasons. But there's an easier way out from, with respect to the theoretical uncertainties, just make the entire star superfluid. And so we find that rather than sort of tweaking the masses and to fix the direct ERCA process, for each of these stars, it's much easier to just ensure that the neutron triplet superfluidity pervades the star. Okay, and so this is what we find in this particular case. So we have learned something about this new Bayesian inference, not just the equation of state, but information on the neutron to proton ratio and the superfluid gap. I also want to point out at the end, there's a direct relation of all this equation of state and composition stuff to neutron star mergers through, we originally created this SFHO equation of state. The purpose of creating this back in 2013 was that neutron star radius measurements were directing us to a mass radius curve, which was inconsistent with the input in previous equations of state. It doesn't matter for the R process abundance so much. However, the amount of mass ejected at least was found in this particular paper to be strongly dependent on the equation of state. And this means that SFHO turns out to be a little bit better about producing an R process in a merger. In any case, to summarize, we've constrained the radius of a 1.4 solar mass neutron star, but low and high masses, the story is a little bit different. There's an interesting future, but in combination with all of these things. But if we combine this with neutron star cooling constraints, we can get composition. And of course, I think there's exciting stuff just around the corner, and it's going to be a good year. Thank you.
Thank you, Andrew, for this great talk. Are there any questions? Please again, raise your hand or write it in the chat. And while we wait for other questions, I had a question to your parameterizations that you showed in the beginning. I mean, they do not only give different radii for different masses, but also the slope seems to be different, right, in the MR relation. Do you know why that is?
Exactly, yeah. This is just simply because sorry, let me go back. The 4L, the line segment parameterization tends to more, have a preference for phase transitions. And so you end up with this, something that looks like, there's no nuclear theory in here really, so I can't tell you what it is, but it looks like a phase transition and then it recovers. Yeah. Okay.
William had a question. Oh, sorry.
No, it's okay. We're answering the same thing. So I see Will Newton has a question. Which nuclear matter parameters are the posteriors you use from nuclear theory and masses and radii over which? So Will, is that the mass radius stuff or the cooling stuff?
That's sorry, I meant nuclear masses and charge radii.
Oh yeah, we use lead 208 and zirconium 90. We can't use they're sort of doubly magic or partially magic, and so we can do them, and they're not too small, so we don't believe our mean field results.
So what are the so when you get your posterior from that data, what equation of state parameters does that inform?
Oh, so the Hartree calculations inform effectively all the equation of state parameters at low density, because we use this. So we use quite a few parameters in, for example, our relativistic mean field calculation. So I think there are about a dozen parameters there which are impacted by the nuclear structure calculation.
Thanks.
Yeah.
Okay. Prakash, you raised your hand.
Yeah. Andrew,
Yes.
when you say make the entire star superfluid, triplet superfluid dominated, did you have a particular density dependence in mind, or it's a constant?
Yeah, that's a good question. So for this particular work, you know, you and I and Danny and Jim have a lot of papers on this where Danny uses something that looks like a Gaussian for the critical temperature as a function of Kf. And so for our particular paper, we just took this same density dependence. It's a 3-parameter model with a Gaussian in Kf. And we have those 3 parameters for each pairing channel.
So the strength decreases as a function of increasing density.
That's right. But also at low densities. And then I see Jerome has in chat, the composition you extract fits with the beta. Oh, so this is confusing because I talk about polytropes, but then I switch at the end. And Jerome, just to explain, for the neutron star cooling calculation, because we need composition, I can't just use polytropes. I have to use a full mean field model.
Okay.
Yeah,
thanks again.
Thank you, Andrew. But the question is it consistent between the different analyses for the cooling and the gravitational wave, for instance?
Yeah, no, we're just adding. I can't answer this right now. We're just doing that now.
Okay, great.
Thank you.
Thanks again, Andrew.
Yeah.
And let's move on to the next talk. Great. The next speaker is Tyler Gorda from the TU Darmstadt, and he will talk about multi-messenger constraints for ultra-dense matter. Please take it away.
Okay, thank you very much for the introduction. I'm primarily today going to be talking about a subset of results from our archive paper that we put up last month. And this is work that I've done in collaboration with a few long-term collaborators of mine and a few new ones who do numerical relativity, which I think it will become clear throughout the talk why we brought them into the mix. So let me just give you a bit of background about the philosophy and approach that we use in our papers. So I'm interested, like many people, in extending the neutron star equation of state beyond the low density nuclear regime where we have good chiral effective field theory calculations to higher densities where neutron stars live. But I'm also interested in folding in knowledge about the fact that the equation of state of ultra dense matter goes over to the perturbative QCD equation of state at very high densities. So in terms of the pressure and energy density plane, there's a region where we have good controlled first principles calculations at low densities, and also a region at high densities where we have similar control. And I'm interested in asking how can we fill in this middle region in the most robust way and most robust and conservative way as possible. So what we effectively do is we use a parameterized EOS ensemble approach in the middle to try to determine all allowed behaviors of the equation of state between these two constraints. And like I said, we want to be as conservative as possible. So we're not interested in doing a Bayesian analysis to try to find the most likely region in the middle. We really want to sweep out as much of this uncountably many equations of state, as Andrew was saying, in the middle, to try to get a region where we have very good confidence. We can say the actual equation of state of nature is inside of this region. So what we do, the most recent work that we've done, we're using a speed of sound interpolation method where we pick a few, about 5 or so speed of sound squared points as a function of chemical potential. We vary the chemical potentials and the speed of sound points randomly and connect them. The interpolation routine we use is to just connect them with straight lines and then integrate that twice, essentially. I have some backup slides on this if people are interested, to get the allowed, a given equation of state. And here what I'm showing is the allowed region color-coded by the maximum value of the speed of sound squared obtained at any density along the equation of state. And the lower speed of sound squared are shown on top of higher speed of sound. So everything really here is colored yellow underneath if you were to take everything off of it. And then these darker colors, which are more restrictive, are smaller and smaller allowed regions placed on top of it. So you can see that we even find subconformal equations of state where the speed of sound squared is always less than a third. They're sort of very hard to construct in some sort of frequentist sense. There's not very many of them out of the few 100,000 equations of state. There's something like 200. But again, since we're interested not in doing a frequentist analysis currently, we just show them here. We've also, in past work, have shown that the boundary of this region is robust against changing to, say, piecewise polytropes. There's, as we heard a few days ago, the piecewise polytrope speed of sound is a little not so well behaved, and so it doesn't match up perfectly if I were to make the same speed of sound color coding for polytropes, but you still have the same general effect, and you have the exact same allowed region. There's a figure in one of our papers showing that's exactly the same. So we do a good job of really filling out everything that's possible. And what I want to say in addition that we have done in the past is, using this approach, we have now some evidence for quark matter cores in massive neutron stars. And we have in our paper some arguments more sophisticated than this figure that argue that this softening in the equation of state band can be identified with the deconfinement transition, especially for the, we find generically for equations of state with low maximum speeds of sound less than c(s) squared, less than 0.5 at all densities, to have these large quark cores, meaning that the TOV stars are on the right-hand side of this this softening, and the matter in their cores is more consistent with quark matter properties than hadronic matter properties. And here, what I'm showing in this figure is just a bunch of nuclear matter models in black, and extrapolation of PQCD, or conformal equation of state down to lower densities. You can see that they cross at roughly the same point where this bend happens, which is just sort of a suggestion for why this identification might not be crazy. But again, there's much more detailed analysis in our paper than I'm showing here in this figure. So this is what we have done in the past, and also all that's gone into that figure that I just showed you was the two high and low density constraints from theory, that the TOV mass for every equation of state in that ensemble is greater than or equal to 2 solar masses, and that the lambda tilde constraint coming from GW 170817 is satisfied for the low spin priors. So those are the only things that we require for each equation of state in that ensemble. And I think many of you know, they nicely cut out different regions at low densities. The 2 solar mass constraint forces the equations of state to be stiffer at low density, and the gravitational waves force it to be softer at low densities. And also in this figure, I'm just highlighting the fact that there are some very extreme or phase transition-like behaviors in some of our equations of state. So our ensemble method does generate a lot of different types of equations of state, and some of which look very much like phase transitions, but they're all technically a little bit more smoothed out by the way we construct them. So the question now is, are there any other robust constraints that we can use within this analysis? And the one I'm going to talk about that we have in our new paper is these following two, namely that a black hole was formed in GW 170817. I'll refer to that as the black hole hypothesis, or possibly with a hypermassive neutron star formed first, which I'll refer to as the hypermassive neutron star hypothesis. So these are things that have been talked about by others also, but as will become clear in the next few slides, we implement them in a different way, which is a bit more robust. And also we want to fold in some radius constraints from the new nicer XMM results from J0740. And the way we choose to do that, because we want to be as conservative as possible, is to use the 1 sigma lower bound, where we just sort of round it to 2 solar masses instead of 2.01. So we require that the radius of a 2 solar mass neutron star is greater than, we pick 11 kilometers, which is the average of the 2 sigma lower bounds from the Maryland and Amsterdam groups. One of them was 11.1 and the other was 10.9. So they're already pretty close to each other. And also in the paper, we talk about some other things that I won't have time to talk about here, unfortunately. So I urge you, if you're interested in this other gravitational wave event or looking at future measurements, how they would further carve away at this allowed equation of state region, I urge you to take a look at some of the figures there. And there also will be as backup slides here if you want to just check out this talk after. So the first of these, or rather the second of these, is very straightforward. We just look at the radius of a 2 solar mass neutron star for any one of the equations of state in our ensemble, and we say, is the radius greater than 11 kilometers? We only are interested in the lower bound here because the upper bounds are already satisfied by the gravitational wave constraints within our construction. The nicer upper bounds are already too large to add any new information. But this other sort of multi-messenger constraint coming from the fact that we saw an electromagnetic counterpart is a little bit less straightforward, and I'll walk through the way that we actually implement it, because in particular we don't want to use quasi-universal relations in our analysis. One, because that's sort of already been done in the literature, but more importantly, these are known to be violated for equations of state with first order phase transitions. And also we have very large allowed behaviors within our ensemble. And so we know that there are many equations of state that we're dealing with where the quasi-universal relations are just violated and we don't even know how badly they're violated. So we can't say robustly how, basically we have unknown uncertainties if we were to use them. So we want to get around using that. And what that means is we have to think about the possible evolutions of this event as a function of the mass of the binary. So like Ben showed us on Monday, there's a few different special masses that are important for a given equation of state. Each of these depends on the equation of state. Particularly, there's a threshold mass for prompt collapse above which, if you had a binary with mass larger than that, it would immediately collapse to a black hole. You wouldn't get an electromagnetic counterpart, and that's in tension with what we see from GW 170817 and the corresponding electromagnetic counterparts. On the other hand, if the mass is too low, there's also tension, because then you just don't form a black hole, because you have enough mass to just be supported by in a neutron star. In fact, even a non-rotating neutron star would do the job. And so you wouldn't get a black hole, and then there would be nothing to really power the other electromagnetic counterparts that we see. And then in between, all these stars are supported by rotation, either uniform rotation or differential rotation. And this crossover point where you have the maximum mass possible with uniform rotation is known as the supramassive limit, and a hypermassive neutron star is what you have with mass above that if it's still being supported by differential rotation. So as I said, all of these masses depend on the equation of state, but some of them are much more difficult to calculate than others. The threshold mass to prompt collapse in particular is you have to do merger simulations. That's very computationally expensive, and it's not something we can do. It's not something anyone can feasibly do on the few 100,000 equations of state that we have. So we can't, unfortunately, implement this equation of state by equation of state. But these other these other masses are easy to compute. I mean, everyone can compute. I mean, everyone can compute both of these essentially. The TOV limit mass is easy to compute, and the supermassive limit, if you have a hydrostationary GR code, is also easy to compute. And that means that we can easily compute and implement a black hole hypothesis requiring that the mass of the remnant was at least the TOV mass, because otherwise we wouldn't have a black hole possible. And the hypermassive hypothesis requires that the mass of the remnant is greater than or equal to the supermassive limit. Again, to be consistent with the electromagnetic counterparts, it would make the most sense to also demand that they're less than this mass, but that's just too computationally expensive for us to do. So what we have done is we're going to look at these two things, and I'll just remind you that something around the supermassive limit seems to be the most consistent with what we see from the electromagnetic counterparts. So in some sense, this black hole hypothesis is really a lot more conservative than is indicated by the full multi-messenger picture of the event. And the hypermassive neutron star hypothesis is probably a bit more in line with it, but it's not entirely clear whether the mass was exactly at the hypermassive neutron star, sorry, at the supermassive limit, or just very close to it. And so we just keep that in mind when I show you those figures. So now one other technical point is that it's not the gravitational mass of the binary, the initial stars, that just sum to give you the mass of the final remnant. If you just took two 1.4 solar mass neutron stars and combined them into a remnant, the remnant mass, because it would be more gravitationally bound, is actually less gravitational mass. But it's the rest mass or baryonic mass that is conserved. And so you can just, the baryonic mass of the remnant will be the sum of the two baryonic masses of the binary components and subtracting off any ejecta that we saw. There are estimates, pretty good ones, for the at least upper bounds on this mass of the ejecta, but to be more conservative, we can just ignore that and just say that all of the mass went into the remnant. That gives you a more conservative bound, in fact. So concretely, the algorithm that we use is to demand that for the chirp mass fixed to what LIGO Virgo observed, there exists a mass ratio in the allowed mass ratio range that gives you a remnant baryonic mass for that Q value that's greater than or equal to this critical baryonic mass, either the TOV or supermassive limit mass, depending on whether you want to implement the black hole hypothesis or the hypermassive neutron star hypothesis, and also that the lambda tilde for that same binary initial configuration is less than 720 if you're using low spin priors.
Tyler, you're at the 15-minute mark.
Okay, thank you. So we also look at high spin priors, which I'll just flash later on if there's time. And then we additionally fold in these radius constraints of two solar mass neutron stars. So now let me just show you the results figures. So what this is the black hole hypothesis, which is the most conservative one again, and then plus these J0740 constraints on radius of either 11 greater than or equal to 11 kilometers, which is the average of the two sigma lower limits, or 11.4 or 12.2 kilometers, which are the two 1 sigma lower limits from the Amsterdam and Maryland groups. The first thing, the black dashed lines here are what happens if you don't implement either of these two additional inputs, but only the two solar mass and GW 170817 lambda tilde constraints. So first point is that the black hole hypothesis is effectively just a TOV cut at 2.53 solar masses, which is different than the about 2.7 solar mass if you were just to use the gravitational mass of the initial binary. So it's important to go through those steps that I outlined before. And then the important point is that the left-hand column here is really our new main result. So this is the most consistent or the most conservative equation of state and mass radius regions consistent with these now 4 inputs. In particular, these two additional inputs are mainly cutting off the very extreme equations of state with high speeds of sound. The lighter colors are being restricted here and the darker ones are not. Since the lower speeds of sound are the equations of state that generically lead to quark matter cores in our analyses, that's not affected at all by these measurements. And in fact, even the most extreme implementation of the nicer radius measurements don't affect the low speeds of sound equations of state at all. Then for the hypermassive neutron star results, we find this. This in terms of the TOV, again, it's sort of like a TOV limit cut from the hypermassive neutron star hypothesis, which is effectively at 2.19 solar masses. That's actually a little bit tighter than what people in the literature had found using quasi-universal relations. And again, this is sort of a more robust way to do it than that. So it's interesting that we find something on the tighter end of things. Here again, since the full multi-messenger picture is a little bit more in tune with a hypermassive neutron star being formed, this is perhaps a little bit closer to what nature requires in order to be consistent with these two inputs. And I'll just again point out that these low speeds of sound here are not affected at all, even in this most extreme case where we implement 12.2 on the hypermassive neutron star hypothesis. So again, even quark matter cores are completely consistent with all of the possible ways of implementing these two results. So they're not cut out at all. They're completely consistent with everything that we see. So I'll just say that even other ways of implementing the this constraint using high spin priors, for instance, or using high spin priors or anything like that, you still just find TOV cuts on TOV for implementing these black hole or hypermassive neutron star hypotheses. There's a table in the paper as well if you're interested in all of these numbers. So it's again consistent with roughly what others have found, but the numbers are a little bit different. So let me just flash my conclusions now and point out that we're still completely, quark matter cores in massive neutron stars are still completely allowed by everything that we have just folded in, the most robust astrophysical inputs that we can fold in. There's more discussion in the paper about, as I said, so you should please take a look at that if you're interested. And I'll just leave these most robust allowed regions here on the slide. So thank you for your attention.
Thank you very much for this very nice talk. Are there any questions?
May I ask? Have you analytical description of the strong interaction on the distance between nucleons? My old question.
Mm-hmm. Yeah, so we don't have anything like that here. Really, there's no microphysics. So even though we can place bounds on the equation of state here like this, we don't have any microphysical description of what's causing the equation of state to fall within this band. So we can't say anything about those sorts of questions, unfortunately.
How is it you calculate a very difficult object without such simple picture?
Well, so what we use is a simple interpolation. So we write down simple equations of state in between, but we don't come up with a simple physical model for what makes that equation of state manifest.
I see. Thank you.
Yeah.
Okay, Sabrina Hood has a question.
Yeah, thanks, Tyler, for this really clear talk. I just have a question or more comment on the threshold mass, which, if I get you correctly, you didn't implement this upper limit because you need simulation. So from neutron star mergers for this, I'm not completely sure, but I think that didn't Andy Bauswein and collaborators give a relation for the threshold mass, which only depends on the maximum mass of the neutron star and its radius of a 1.6 solar mass neutron star. So couldn't you also use this as a constraint?
Yeah, so this is a good point. There is such a relation. We're pretty wary about using a universal relation, even with more parameters like that. Because we really have quite exotic equations of state in our ensemble. One of the things I am interested in looking at, though, is whether we can calculate the threshold mass for Planck collapse for some of our just sort of randomly selected more extreme equations of state and see whether that universal relations holds or not. It's something we could do, but again, I would be worried about unknown systematic errors because our equations of state might be, some of them might be too extreme for that to hold.
Yeah, okay, that makes sense. Thank you.
Are there any more questions? If not, thank you again. And let's move on to the next talk. Antea, could you share your slides?
Yes, I'm trying it.
Thank you.
You can see.
I can see the slides. Yeah, but they're not in. Yeah, now they are on full screen. Okay, great. So our next speaker is Antea Fantina, and she will talk about neutron star crusts at finite temperature.
Thank you very much. Good afternoon, everybody. And yeah, we'll move to the topic of the neutron star crusts at finite temperature. So I will go down in density. So first of all, thanks very much to the organizers for inviting me. And so the topic is, as I said, a neutron star crust at finite temperature. So for sake of time, I've selected some recent results. And I would like to discuss in particularly 2 points. The first one is impurity in the neutron star crust. And the second one, I will say a couple of words on the pasta phase at the bottom of the inner crust. So every one of us know that neutron stars are formed hot from Quark supernovae, as it's sketched here. So you can see that at formation, their temperature is well above the MeV until they cool down, reaching finally their ground state catalyzed composition and structure. So if we look at the temperature profile at crystallization in the crust, we can see that this is about at most 1 MeV, so a few hundreds of keV, at most 1 MeV. And this is at the point where the crust forms, which means when it solidifies. Still, it's a finite temperature, so we do expect to have an ensemble of nuclei present in the crust. So the question is how to approach this kind of problem. So from the theoretical point of view, we have powerful ab initio methods, but unfortunately, they are not affordable for inhomogeneous matter in all the thermodynamic conditions explored. Therefore, we have to rely on more phenomenological models. So for the talk, I will show you some results that are rooted on the nuclear energy density functional theory. The second point is automodel clusters. So one can use the so-called one component or single nucleus approximation, where you basically resume your full distribution to one representative nucleus. So your energy minimization gives you the favorite clusters in the crust. However, if you do consider the full distribution, this means treating the system in a multi-component approach. And so your energy minimization procedure should give you the favored cluster distribution. And you can see here the expression for it, which looks like a psi equation, but is not. Indeed, we have terms like this one here that account for rearrangement terms. So I won't have the time to go into the details, but I will say a couple of words later on the importance of this term. So this kind of approach is okay when you're looking at average thermodynamic quantities, and also if you look at zero temperature. However, as soon as you go at finite temperature, one should really consider the full distribution. And also this kind of approach is needed if you want to compute reaction rates or cooling that depends on impurities. And I will come back on this point later. So as I told you, we see here, I show you here the nucleon number as a function of temperature. So as I told you before, this one component approach, this is solid line for a given density, but the similar things can be said for different densities. So at almost zero temperature, results using a one component approach or a nuclear statistical equilibrium, which means a distribution of nuclei, give you basically the same results. However, as soon as you move at finite temperature and even below 1 MeV, the prediction can be very different. So really, the ensemble of nuclei is expected to be there and gives you very different prediction for the edge-range cluster. And typically, what is assumed is that the crust crystallizes, so solidify at a certain temperature, after which the composition is frozen. And then the full equilibrium is maintained until the ground state. However, this is unlikely to be the case. And if the cooling is rapid enough, then the composition might be even frozen at higher temperature. Or maybe other reactions are possible below the crystallization temperature, which means that the composition can be different from the ground state one. And what for sure we can expect is to have the coexistence of nuclear species, which means impurities. And this means that given that the crystallization temperature is not so high, we do expect that the static properties like the equation of state or composition is similar to the zero temperature one. But this might not be the case for dynamic or transport properties. And indeed, cooling simulation typically use the ground state, equation of state and composition, but recast the nuclear distribution in an impurity factor, which is usually a constant free parameter adjusted on data. And we can see here from this simulation by Vigano and collaborators that the evolution of the magnetic field or on the thermal luminosity, if we use different impurity factor. For example, if you look at same mass here, it's green, blue, and black lines, and we see that there is a considerable difference in the evolution of both magnetic field and thermal luminosity. So the idea would be having a consistent calculation of both the nuclear distributions and the impurity factor, and of course, the associated transport properties. And I will show you some results on this just in the following slides. So as I said here, for the equation of state and composition at these temperatures, one might expect not to be too different from the zero temperature one. And I show you here in what we can expect actually. This is for the outer crust, so where the crystallization temperature is lower. So you see here is a few hundred of keV along the crust, and we see here the composition. So at the crystallization temperature, the composition indeed not very different from the zero temperature one. However, if you think that the composition freezes at higher temperature, say 310 to the 9 Kelvin, then differences can appear, which means that the composition, if the crust is frozen above the crystallization temperature, then can be different from the ground state one. Now, what about impurities? I show you here some recent results on the outer crust and the inner crust for two given temperature and density, just for illustrative examples. So here is the distribution in Z, and you can see here the distributions of in Z of elements. So what we can infer here is that as soon as you go higher in temperature or higher in density or equivalently pressure, you see that your distribution tend to be broader as expected. So you have a broader distribution and you expect to have a higher impurity factor. And if you remember one of the first slides, I told you that the distribution depends also on terms like the rearrangement factor, the rearrangement term. And you can see here that when we neglect the rearrangement terms, you get prediction on the average Z that is very far off the one that you would have if you properly take into account. So this term is actually needed for thermodynamic consistency. Now, this is the impurities, and we have also calculated the associated impurity factor, and I show you here the results for the outer crust and the inner crust. So I don't have the time to go into details, but I sketch you here the result. So as you can see, as I told you before, as soon as we go higher in pressure or density, the impurity factor typically increases, and the same for if we go at higher temperature. Now, what you see here, so this oscillation is a consequence of the more microscopic approach used for the outer crust, while for the inner crust, we have used a compressible liquid model approach, which smoothed the behavior, but the tendency is the same. And you can also see here another striking feature, that is that the impurity factor is not at all constant. Actually, you can see it's a variation of, so an alternation of pure and impure layers, which means alternation of conductive and resistive layers. So we can expect that this might have an impact on transport properties. And actually, there have been some very recent calculation of transport properties from the impurity factor, and I show you here some results from Potekin and Chabrier, where they have calculated the impurity factor for the inner crust. So they do have these alternation, this oscillatory behavior, because they do include the shell effects, but they have an approximated calculation of the abundances with respect to the work I showed you previously, but the idea is always the same. You see these oscillatory behavior of the impurity factor. And what I would like to point out is this effect that you can have on transport coefficient and on the, specifically here, the electrical conductivity. So if you compare the solid with the dashed lines, you see the effect of having an impurity factor that not only is not zero, but is not constant at all. So the impact is not at all negligible. Now, until now, I've assumed the cluster has been spherical. I've not spoken about geometry, but we do expect, one might expect to have pasta phase in the bottom of the inner crust. So there have been some very recent calculation on it, and I will show them here. So of course, when you have pasta phases, it means that you have different geometries, and this of course adds a complication in the calculation because your probability now do depend on the dimension. 3D, of course, if you have spheres, or cylinder 2D, or slabs, or the inverted configuration as well. And what it has been done in this work is to calculate distributions for the different pasta configuration. And what we can see here is that there is actually a competition among geometry, and which can coexist in the large fraction of the pasta phase. And also what it has been done here is to calculate the variance. Well, I told you that the impurity parameter is basically the variance of the charge. And when you have pasta, since this can be dependent on the geometry, if you have a probe, these see different things if you have spheres or cylinder. So it depends on actually the section that the probes encounter. So it depends on the geometry. This is why the charge fluctuation has been calculated for different planes. And you can see here the impact that this might have. So therefore, one can expect that this has consequences for transport coefficient and transport properties. Now, this work has been done using for the bulk energy some relativistic mean field model. And I would like to spend a couple of words on the model dependence that one can have when one computes the pasta phase. I will show you here some example at 0 temperature, so not yet at finite temperature. This is something in progress. And on in particularly, you see on the left part, this is the sequence of pasta that has been calculated with different models. And you can see here that the trend is the same. The sequence is the same. So it's spheres, rods, slabs, tubes, and eventually bubbles, even if not all models predict bubble. So apparently pasta phase is robustly predicted. Still, there are model dependencies. And what I would like to show on the right panel is a full Bayesian analysis on the density and pressure of the pasta transition. So this means this transition here. So this is not only with these 9 models, but it's really a full Bayesian computation. And what I would like to draw the attention is of the effect of these low density filters. So what does it mean? The difference between the blue and the, say, orange curve is that the filter on the low density part of the functional is applied in 2 different density regimes. So if we filter from very low density, this is the blue, basically all the models that predict a transition to the pasta phase relatively early, are almost all filtered out. And you see it here in the prediction of the pasta observable. So this is the fractional pasta thickness with respect to the wall crust. And this is the moment of inertia of the pasta with respect to the wall crust. Similarly, plot can be given for the mass. And you can see here, as soon as you filter from very low density, almost all the models that predict zero pasta are filtered out. So one should expect to have pasta. So typically, when one speaks about global properties of neutron star, is the high density that counts the most. But for crustal properties, actually the low density also counts. And as I said, these are zero temperature, but finite temperature is in progress. And you can see here also that the impact of the pasta layer, which means it's about half of the mass of the crust, same for the moment of inertia, and about a tenth of the radius. And some results also on the pasta and the mass and the radius of the pasta are given also in this very recent work from Bayesian, Newton, and collaborators. So I wrap up here. I show you some results for the crystallization properties of neutron stars. I showed you the importance of nuclear physics constraints, especially on the pasta phase. I didn't have the time to address the importance and the correlation with bulk and surface terms, but I'm happy to answer if there are any questions. And one of the take-home messages really that one would really need the consistent calculation of the distribution in the crust in a full the distribution approach, namely a multi-component approach, and of the impurity parameter. And of course, to compute this consistently with the transport properties. The results that I showed you on the impurity parameters are also available, publicly available. So if one wants to compute cooling simulation with them, just you can just download them. And of course, the next step is really to have consistent calculation of the transport properties. And as I told you, this impurity factor can be increased if pasta is considered. So this might be something to look at more deeper. And I thank you for your attention. I take questions.
Thank you very much for this great talk and for being perfectly on time. Are there any questions? Please raise your hand or write something in the chat. And while we wait, let me ask something. Yeah. So I think it was slide 12 where you showed the different equation of state models or the different functionals, and you showed where the different pasta phases, right, and where they appear. So you say that there are some models where not all phases appear, but what exactly does this depend on? I mean, which parameters of the model determine, for instance, if you see tubes and bubbles?
Well, I think the sequence, of course, the sequence of pasta, these maybe depend on the details of the functional, both the surface and the bulk. I can show you some, if you want some correlation. Actually, if I have it here, I can share. Okay, this is for the radius, so it's not really what I may have also the one for the transition from, let me check if I have it, I'm not sure. No, so we have it in the paper, but there are indeed some correlation on the density between the spherical and non-spherical pasta on some bulk properties. I'm trying to see if I've put it in my backup slides, but I only only have here the one for the pasta radius. But you do see some correlation with both bulk and the surface. So the surface also is very important.
Okay, thank you very much. Then there's a question by Prakash.
Yes.
Do you want to ask it?
Could you please expand a bit on the structure and size of the rearrangement term?
Oh, yes, I could. I can. This is basically comes from the fact that you have the charge conservation. And therefore, when you do your density minimization, you have additional terms that are related to the derivative of the, specifically the interaction part of the free energy on the density. So when you have different cells, because we are in a multi-component approach, so you have different cells. And when you do your minimization, the cells are somehow depend on one another and depend on the density because of the charge conservation. So, therefore, you have this extra term in the free energy that enters in the probability. I could show you the equation and of course formulate a bit more, but substantially is that.
What's the size of it?
Oh, the size, it's not very big. This is why most works have been neglected. So the size is not big, but since you are looking for minimum, then the effect can be substantial on the composition. But the size, I would say, is not is small with respect to the other terms in the energy. Nevertheless, is needed. Otherwise, you wouldn't find the correct average and most probable nucleus in your distribution.
Thank you.
Okay. If there are no other questions, let's thank Antea again and move on to our last talk of the day. Albertina, could you share your slides, please?
Yes, I'm
awesome. I see them. Yeah, very good. Okay, that works. Great. So our last speaker of the day is Almudena Arconis from the TU Darmstadt, and she will talk about the R process connecting simulations to observations. Please go ahead.
Thank you very much. Thank you also very much for giving me the opportunity to talk here. I will change a bit topics and talk more about observations, but not about the kilonova. I was talking about the kilonova many years ago after our paper of 2010, and people were thinking the R process does not occur in neutron star mergers. It should occur in Quark collapse supernova. So today I would like to talk a bit other kind of observations and how can we use them. So you know the R process is the rapid neutron capture process. So we need something rapid, something explosive, and we need a lot of neutrons. So neutron stars and explosions produce the R process, and that's why supernova and neutron star mergers are the favorite candidate to explain the origin of heavy elements. So how do we investigate that in Darmstadt? So we do supernova simulations, Quark collapse supernova simulations, where neutron stars are born, and we also simulate neutron star mergers. So this is a simulation of Federico Garcinella and Max Jacobi. And what we do with the simulation is we explore also microphysics. So we explore, for example, the equation of the state that we have been discussing these days. Also, the impact of neutrino and neutrino reactions at high densities are very important, but they were not touched so much here. And then what we do with our simulations is we take the matter that it's been ejected, and then we follow the evolution of density and temperature. And at every density and temperature, we can calculate which nuclear reactions take place. And this is the nucleosynthesis that, of course, depends on the nuclear physics of the extreme neutron-rich nuclei that are involved in the R process. And what we want to do is to use observations to compare or contrast our nucleosynthesis calculations. And with these observations, we want to constrain the simulations. And in that way, we constrain two things. One are the astrophysical conditions. For example, we may be able someday to constrain the rotation or the magnetic field of a supernova that was given a given composition, or also in the neutron star mergers. We can also constrain if we have two neutron star and neutron star a black hole. So we were also hearing about that on Monday. And also what is interested in this workshop is the microphysics, the equation of a state. So I have just one slide that I want just to pass the topic to someone else. And then I will focus more on the observation. So here we have explore the impact of the equation of a state, and I would like to suggest, if you want to know more, to ask Sabrina Hood, who was doing this project together with Hannah Yassin. So they have done performed hydrodynamical simulations, 1D simulations with a flash code and very good neutrino transport. And they increased the energy deposition by neutrinos in the gain region. So the proton neutron star was untouched. And what they found is that they explored the contraction of the neutron star with different equation of a state. So this is the radius of the proton neutron star as a function of time. And here is the radius of the shock that, of course, also reacts. And you have here the Latimer density, the typical 220 equation of a state that has been used since many years, and the Shen equation of a state. And you see that the radius of the proton neutron star are very different, and they found out why this is different. So Sabrina can tell more about that. And the quantity that rules the contraction of the proton neutron star is the effective mass. So they changed the effective mass. So they were always using the Latimer functional, and then changing only the effective mass from 0.2 to the Shen value. This is 0.634. And you see that this is exactly what changed the contraction of the proton neutron star. And Sabrina and Hannah also changed the incompressibility, the symmetry energy. So they changed several things, but the main quantity that impacts the contraction of the proton neutron star is the effective energy and the effective mass, sorry. And Sabrina can also explain more things in the discussion session or later, or if there is some questions, she can just answer. And of course, Sabrina has also calculated mass radius relation. I felt I have to show a mass radius relation for all the equation of states that Sabrina was producing. She calculated also a mass radius relation. But now I want to, as I say, change topic, and I would like to talk about observation and how can we use observations to constrain the simulations if we manage to reduce the nuclear physics uncertainties. So one observation that has been done of the R process that you have all probably seen is a strontium. So this is the wavelength, so this is in the flag. So this is the spectrum of the kilonova, and this feature here is due to a strontium. So observing abundances of elements in a spectrum, we can get information about the condition and of what is going on in the environments that produce those elements. This is just like one event, a kilonova and one element. So we would love to have more information so we can look at the stars in general. And it's kind of a multi-messenger signal where we look at no light. So we look at absorption lines. So these absorption lines, as you see here in the spectrum of the sun, are due to the atoms that are in the atmosphere of the sun that absorb the photons at a given wavelength. And depending on which element you have there, you're going to have different absorption lines. And this tells us what is the composition of the photosphere. And this composition, it was the composition of the molecular cloud where the sun was born. We have, of course, more information in the solar system, and this comes from meteorites that I will mention later. We can look also at other stars. Unfortunately, we cannot look to the oldest stars, the first stars, because they had only hydrogen and helium, but they are already gone. They are already dead, right? And they produce some metals, so elements heavier than helium, and put them into the interstellar medium where new generation of stars form. So after one of those or two of those cycles, we have very, very old stars. So they are very low mass stars that evolve very slowly and they are still alive, and we can observe those. And if we go many times through this cycle, then we have something like our sun. And if we look at the spectrum, we see something like that. This is again the wavelength, so a spectrum of the different stars. So for those stars, we would have a flat spectrum, no absorption lines, there are no metals. If we look to a very old star, we have this and this spectrum where you see there are very few absorption lines, there are very few metals. So they are metal poor stars. And this is the spectrum of our sun where many processes, many events are mixed together. So we look at abundance observations from stars, and we can do two things. One, we can look at the evolution of abundances as a function of time or as a function of metallicity. So low metallicity, not many metals, those are the old stars, so this is the past, and high metallicity, a lot of metals, these are stars like our sun, like today. And doing this, we can use galactic chemical evolution and try to understand what are the R process sites. So I believe there are more than neutron star mergers. And here is a kind of proof that show you that we need something else in addition to neutron star mergers. This is a work led by Benoit Kotek. And here we have a ratio, europium over iron, as a function of metallicity. This is the iron amount, and this is like time. So this is the past. These are very, very old stars, and this is the sun is 0. So this is the astronomical way of giving ratios. It's like a square bracket, means that it's the abundances, the ratio of the abundances in the star minus the same ratio in the sun. So this means it's 10 to the minus 3 times the iron that we have in the sun, and here the 0 is the sun values. So what we see there is europium, that is a typical R process element, very early in very old stars, and there is a lot of scatter. The scatter tell us it was a rare event, not like a supernova, that it's something very frequent. And we see also that it goes here more or less flat and then goes down. So this is very interesting. And we can explain that looking at the production rate as a function of time. So here we have the production time of iron. And this iron is initially produced in Quark collapse supernova, and then later in type 1a supernova that comes from the thermonuclear runaway of white dwarfs. And since those come from low mass stars, evolve slowly and come later, but this is the iron production that we know it's like that. Then we know how this ratio should look like. So it should be flat and then going down. This is what we observe. This now is a function of time. And we can say, if we want to reproduce this trend, we need this black line for the production of rate of europium. And what do we have from mergers is the dash line. So the dash line will produce this trend that is not what we observe. So what we observe of europium is telling us there is something missing in addition to mergers. And here we have marked it with this purple line. And this is telling us that there should be something occurring fast enough and early enough, putting enough europium before the type 1a start to put also iron, so that we manage to get this going down. Okay, so there is also another way of using abundances to constrain and to understand the R process conditions, and this is using patterns or ratio. This is a game we did many years ago with Camila Hansen and Fernando Montes, and it was barring the astrophysical conditions. This is just an example in Quark collapse supernova, neutron-driven ejecta, so the electron fraction, the neutron richness, and also the entropy. And the regions marked here with these lines are the regions where the strontium over yttrium ratio that we get from our calculations was agreeing with observations. And these are the other regions where the other ratios are reproduced. So this was a way of looking at observations and trying to constrain the astrophysical conditions. Of course, this cannot be done like that because we know there are more astrophysical conditions and there are the nuclear physics uncertainties. And there, Julia Bliss, who was PhD student in my group, made an amazing work looking at all possible astrophysical conditions and also the uncertainty from nuclear physics. And then only like playing with all these things together, we are going to be able to link the observations to calculations. Only if we also identified what is the key nuclear physics and we reduce the uncertainties there. Okay, so these are the ways of using observations to constrain the simulations or to constrain the astrophysical conditions and the microphysics that we put there. So let me show you a few more examples. This is a paper that appeared in Science beginning of this year, also from Benoit Cotet with Maria Lugaro, and the calculations here are from Marius Eichlam, and there was a very big and very nice collaboration, and with a lot of nice discussions. We learned a lot. And this was looking at our process in meteorites. So meteorites are great because they give us information about isotopes, not about elements, but about isotopes. And they tell us what was the composition or what was the event that contaminated by the last time the cloud where the sun was born. What was the last R process event before the sun was born? And this was done looking at ionite and chromium, and they are, this is ionite is in the second R process peak, and this is beyond the third R process peak. So it's really interplay of two elements that are quite extreme and are process isotopes. And this is what this line is what the meteorite abundances tell us, that this ratio should be like that. And then we say, okay, let's do our calculations and compare to that ratio. So we tried different astrophysical scenarios that was done by Marius, and he tried like neutron star mergers. This is the dynamical ejecta, and also the ejecta from disk after the neutron star merger. And he also tried magnetorotational supernova. So let me say something about that. So I was saying that we need something else in addition to neutron star mergers to explain the evolution of the R process in our galaxy, and perhaps also in other galaxies. So let me say this is an exciting possibility, the magnetorotational supernova. So I assume this community believes there should be supernova exploding with a strong magnetic field and producing pulsars. So I don't have to justify that. But what I want to say is that the normal supernova are driven by neutrinos, and neutrino transform neutrons into protons, and this kills the R process. But if we have a strong magnetic field, it could be that part of the matter is ejected by the magnetic field very fast without changing neutrons into protons. So this is something that it's been investigated now for some years. So there were some 2D and 3D simulations with some simple neutrino treatment. And the one here corresponds to the simulations of Pintela et al. And now we have also calculated the nucleosynthesis based on simulations with accurate neutrino transport. The simulations are from Martin Obergaulinger, and the work, the nucleosynthesis, was done by Moritz Reicher, who was doing the PhD here in Darmstadt. And they found a very, very broad nucleosynthesis. So we R process, neutrino P process, R process. So here you see 4 different models with different rotation and magnetic field. And just want to tell you the red line is the one with the strongest magnetic field. And in this one, we find R process. This was also found in other simulations, but not with a good neutrino transport. So we see neutrinos are still playing a critical role and should be treated properly. Of course, these were 2D simulations that we used. Now we are looking at 3D simulations because only last year, the first 3D simulations with accurate neutrino transport with magnetic field were reported by Martin Obergaulinger and Takami Kuroda.
At the 15 minutes mark. Okay. So here we have the environment, and then we have different points here and even lines. So you see here the points. So these are different pieces of mass that have been ejected with the slightly different conditions. And at the end, we weight those by mass and we get the solid points that you see here. And there are different symbols and different colors. So they correspond to different nuclear physics inputs. So FRDM is the mass model and Duplo-Zucca is the other mass model. Here we use different beta decays, and the 3 different symbols correspond to different fission yield distribution. So you see there are a lot of uncertainties, but it's a way of combining astrophysics, nuclear physics observation, and try to find out where the R process comes from. And from this study, we could say that the last R process before the sun was born came from the disk of a neutron star merger. Sorry. Okay, so I went in the wrong direction, I think, yes. Here, so I want to talk also about the European stars that are also very exciting to study just one R process event. These are stars that are in fornax. We have found them. It was also work done with Camilla Hansen and Moritz Reicher based on a broader study from Moritz. And now Marta Molero has done the chemical evolution studies based for dwarf galaxies based on this observation. So we have found European stars. Those are stars that have the highest European ever observed in a star. So here you have the abundance of European, again, as a function of metallicity or time. Gray is the galaxy, our galaxy, and light green is the fornax dwarf galaxy that is orbiting our galaxy. And these 3 yellow stars are our new discovered European stars.
And you see, so usually the people talk about reticulum 2. The Anna Frevel is always talking about reticulum 2 stars that have a lot of europium. That's not completely true. So they have a high europium over iron ratio because they have almost no iron. But the ones we have found are really europium rich and at high metallicity. So that's completely new. And we were able to find out that these abundances are only from one R process event, and there has to be related to some star formation in the galaxy. And there is also this black star here, but we check the barium over europium. So barium is a typical S process element. And you see this star is here, and these are S process models. While these are the models I was talking about before also for the R process, mergers, C-scan, magnetorotational supernova, they fit with the stars that we have discovered with these europium stars. So there is a lot of possibilities of using abundances in stars to constrain the astrophysical conditions and the microphysics. So I have no time to talk about also an exciting ratio that is thorium over europium. That was also work of Marius Eisler. And with this, I want just to come to my final slide where I want just to say, yes, great that we can combine everything, and we have this kind of workshop where we can discuss the different ingredients going to them from the microphysics to the observations. I was talking of observations of elements and abundances, but of course we also use this to calculate, for example, the kilonova light curve. And with this, I just stop here and thank you for your attention.
Okay, thank you, Almudena, for this great talk. Are there any questions for Almudena? Maybe while we wait, I can ask one. I think it was slide 8 where you said, I mean, you compared the abundances, right? And you said there was a process that has to happen very early before neutron star mergers. I was wondering, so this residual europium, it goes down again, right? So at some point, this would mean that this process has to subside, I guess. So do you know what it would be that only would happen in the early universe and then just stops happening?
In principle, this would fit with supernova. Supernova occur more early, you see also from the iron production. Also, like this magnetorotational supernova, they need to have quite fast rotation in order to enhance the magnetic field during collapse. And we believe that the stars could rotate faster when they are very old stars. So they have less metal in the atmosphere, they have less mass loss, and they are faster rotators. So all like stars that were born early were able to become faster rotators than stars that are now. So in principle, it would fit with having a magnetorotational supernova.
Okay, thank you. Are there other questions? Okay, because I had another one, that's good. Oh, Sabrina raised her hand, so please, Sabrina, go ahead.
Yeah, for this, at the same slide, I was just wondering, so for the left figure, why are there halo stars that are the old stars and now the younger stars are all disk stars?
Yeah, so usually the stars that are in the disk we have more star formation, and then you have more action going on, so to say, and then you push the metallicity of the stars. So the halo is an old component of our galaxy where we have mainly old stars. There is also, of course, the question where all these old stars come from. And there is also there are also proofs that some of those stars come not from our galaxy, but from other dwarf galaxies that are orbiting around our galaxy, and then just transfer some stars. And this is also a very active field of work, like trying to find out where if those stars belong to some dwarf galaxy and come from a dwarf galaxy that have different history and they are older. So for example, the Magellanic Cloud, they are older stars.
Okay, thank you.
But perhaps there is some question for Sabri.
Okay, I had another question for you, actually. I think it was slide 11 where you talked about the meteorite compositions. Is there a way, I mean, how many events, can you estimate how many events are responsible for the composition in the solar system? Is it one event or is it like a sum of many different events?
Many events. But in this, so in these meteorites, of course, you can also find that, for example, one of the isotopes come from one event and other isotopes come from other events. But these two isotopes have similar decay time. So if you do the chemical evolution of these two, even if so there is a very low probability that they come from a different event because they have the same decay time. So if you take other ones, then it could be that one was produced, like thorium was produced in one event and iodine in another event, and you have both in one meteorite. But for these two, we are in the lucky situation that they have similar decay time, and then this means that you can track back that they are produced in the same event with some uncertainty, of course.
Okay, thank you. Okay, so if there are no further questions for Almudena, I would like, first of all, to thank all the speakers again for the excellent talks today. And I would like to open this discussion session up to questions for all the speakers. So we have roughly, I think, 20-25 minutes of time left in the official program. So if you have any questions, specifically the young people, if you have any questions that you would like to ask of any of the speakers, yeah, now is your time. So please raise your hand or write it in the chat.
May I talk?
Yeah, you can ask the question.
Yeah.
Please go ahead.
Thank you, Chairman. In our non-accelerator experiments, we have measured the dependence of the strong nuclear force on the distance between nucleons in the deuterium nucleus. Therefore, I am very interested in theoretical description of our experimental results. Therefore, I ask my very simple questions. Thank you.
So could you tell us more about the experiment? Where did you do it? And
what is it?
Could you tell us more? I mean, maybe you can tell us more about the experiment and where and when you performed it and what your results were.
Our non-accelerator experiments consist from spectroscopic investigation of the lithium deuterium crystals, and therefore we measured the strong nuclear force on the dependence between nucleons in deuterium nucleus. Do you understand me?
Yes, yes.
Yes? I see. Therefore, I am very interested in analytical description, this interaction. To my mind, it is very interesting task.
Thank you.
Yeah, thank you.
Okay, so I actually have a few questions left, and I would like to go back to Chuck's talk. So I have a comment on the question. So you said that there are other measurements that measure the neutron, or that measure observables that then are used to determine the neutron skin, right? But I just wanted to make the comment that also PREX doesn't directly measure the neutron skin. There's also some modeling involved. Maybe the uncertainties in this modeling are smaller, but maybe they are underestimated. I cannot say this. I just wanted to make this comment. But my question was that there are these other experimental observations that lead to lower estimates for the neutron skin. And there are also a lot of theoretical calculations. And even if you don't trust chiral EFT, which you are free to do, any phenomenological interaction that there is, microscopic phenomenological interaction that there is on the market, predicts pressures in neutral matter that are well below. And of course, the uncertainties are very big. But let's say there was P-Rex3 or P-Rex4, and they would say, they would confirm this mean of L is 110 MeV, and the uncertainty would be smaller. What would you say, Chuck, is the problem with everything else?
So let me put up the symmetry energy plot, and maybe that's a good way to discuss your question. So there are a bunch of different observables plotted here, or these are correlations based on different observables. And let me just comment on one. The blue band, which is very different from the others, is what I would claim is a model-dependent determination of the neutron skin in tin, and this is from proton nucleus elastic scattering. It's a simple model-dependent analysis, and it uses very crude nucleon-nucleus amplitudes. I say that because, in fact, they're very old amplitudes of mine from a long time ago. And this is an analysis by a Chinese group that uses these old amplitudes. And so this particular result is model dependent. So if you were willing to take the blue curve off the figure, then a lot of the correlations based on other nuclear observables like the dipole polarizability or nuclear masses or the position of the giant dipole resonance, they overlap, and if the overlap region extends out to slightly larger values of L than 60 or 70, that's all fine. And so maybe your question is with the chiral effective field theory calculations, and so the most recent ones are the oval bands in the middle, and so I guess Drischler and Dick Fernstall and others are involved in those, and so the question is, are those chiral calculations accurate? Did they really estimate their errors completely and accurately? And that's an exciting thing to check.
That's true. So I just wanted to make the comment that this yellow ellipse is extracted at a different density than all the other constraints, at a little bit higher density. So if you would extract it at the same reference density, it would move further down and agree better with the other constraints. But it's not only chiral EFT. I mean, even let's say chiral EFT is wrong. We have many other microscopic phenomenological models on the market, right? The stiffest one is the argon interaction, which was very successfully used in many calculations also of the equation of state. And also if you add the most repulsive three-body force that was cooked up, which is the Urbana forces, if you add them up, you will never get to these very large values of L. So if this P-Rex value would be confirmed, something would need to be wrong with all our models for microscopic interactions, no matter if they are chiral or not. So I wonder if you have if you would know where you would look for in case this would be the case.
Yeah, I think once you say phenomenological interactions instead of chiral effective field theory interactions, in fact, you have huge freedom for three-body forces. And when you say most repulsive, I think you're incorrect. I think you could have the phenomenological forces tend to have not well-constrained three-body forces.
Yeah, okay, that's absolutely right, of course. But then at some point you sacrifice your repulsion in, if you want more repulsion in neutral matter, you sacrifice agreement with other observables that you can calculate, right? That's what I mean. I mean, you can only do so much, because if you look at it from a chiral EFT standpoint, it's not unlimitedly many interactions that go into neutron matter. Neutron matter is mainly pion exchanges because you cannot have many neutrons because of Pauli exclusion, right? You cannot have them in a small space. So all these model-dependent short-range terms, they are anyway suppressed because you have only neutrons. So you have mostly long-range physics, and that's pretty well understood, I would say. I mean, there is some uncertainty to it, but it's much better understood than the short-range physics. But the short-range physics is not that important in neutron matter. But okay.
So I mean, the 3 neutron forces are not zero. They make
yes.
important contributions to the pressure, and that's what we really want to test. How big are the 3 neutron forces?
Chuck, I want to go back to that plot that I was hung up with. Sorry.
This one?
Yeah. The numbers that you sent me for P-Rex 2 alone is 0.278. And this plot does not reflect the center at 0.278 either. So this must be some old graph. This appears to be centered around 0.25, or should I not be worried?
The dark green line and the upper x-axis, the dark green line is pretty close to 0.278, I think.
Oh yeah, so I should be looking at the green line. Okay, I was looking at the band that was there. Okay, thank you. You cleared it up. Thank you.
Right.
So there was a question in the chat by Rémi Bougot, and it's about, I think the question is to you, Chuck. What about the formation of alpha clusters at the surface of heavy nuclei, and I guess how they affect the extraction of the skin?
So what I measure is the weak radius, so the RMS radius of the total weak charge distribution. And so weak charge can be on nucleons, it can be on alphas, it can be on mesons. If there are a bunch of alphas, that's very interesting. And so by all means, build your microscopic models and try to reproduce the weak radius that P-Rex is measured.
Are there more questions for Chuck or for anybody else? By the way, also, I just wanted to comment to this plot that you just showed. I mean, of course, the correlation is model dependent between the skin and the tidal polarizability, and because, I mean, in principle, these are information that probe the equation of state at different densities, right? So I can make one equation of state that gives me a certain skin of 0.16, let's say, and I can still end up with a 14-kilometer neutron star if I wanted to. So these things are not one-to-one correspondence. But what I wanted to ask, do you have this plot? So for instance, the LIGO upper bound is at 90%, right? 90% confidence. And NICER and P-Rex are both at 68. If I would plot this at 90%, basically there would be no tension left, right? Or if I instead would plot LIGO at 68%, there would be more tension. So, I mean, did you ever? Do you have this another plot where you show them at basically the same confidence intervals that agree with each other?
So I completely agree, and the experimental collaboration worked very hard for their 68% contour for P-Rex 2, and basically the 90% would fill the figure.
Okay. I had also another question for Tyler. Sorry, I'm shamelessly asking all my questions. If someone else wants to jump in, please raise your hand or write it in the chat. But otherwise, I will just go ahead because I wanted to ask a few more. Oh, great. Thank you very much. Alex, you raised your hand. Please go ahead and ask a question. We cannot hear you. I see that you speak, but I cannot hear you. Yeah, that's Zoom.
What about now? Is it
Yeah,
getting
then
better?
now it works. Awesome.
Okay, sorry.
Thank you.
I have a question for Andrew. So you mentioned that you found that your Bayesian analysis favors equation of state that have direct Urca and superfluidity, right? And
well, to say have direct Urca, what I mean is the process is allowed kinematically, but forbidden because of the superfluidity.
Yeah. And then you mentioned that you created SFHO for a better agreement with supernova explosion simulations, but SFHO
actually,
does not have a direct Urca threshold, right?
I believe so the creation for SFHO was to match neutron star radius observations, but I suspect, because I haven't looked at this, and I didn't try this particular equation of state in our neutron star cooling simulations, but because it's a relativistic mean field model, it's a good guess that that has a direct Urca process at some that is kinematically allowed at some point in the neutron star. However, of course, that particular interaction says nothing about the superfluidity. So, yeah.
I mean, SFHO does not have a direct Urca threshold. I checked that, so only at really high densities. So,
oh, really?
So I wanted to ask if you can like modify it to still fulfill all the constraints you were looking for and giving it a direct Urca threshold, if you know how to do that, or.
Yeah, no, that's certainly doable, right? That was unfortunately, so that's just one particular equation of state which matched the neutron star radius data, but there's quite a bit of uncertainty even now with all the multi-messenger constraints we have in the equation of state. I think it should be relatively easy, for example, to fulfill all the neutron star structure constraints, but still have a direct Urca process at any density you would like. And so, but that's interesting about SFHO and the direct Urca. I didn't know that.
Okay, thanks.
Yes, thank you.
I missed that one. What showed direct Urca?
So Alex pointed out that that this SFHO relativistic mean field parameterization that we constructed back in the day doesn't happen to have a direct Urca process at any density.
So well, what is the observational evidence for direct Urca?
Well, this is actually a good question because part of the reason that the isolated neutron star cooling, Prakash knows this, but the isolated neutron star data has by and large relatively large luminosities, and that would tend to suggest that these stars do not have a direct Urca process going on. I think the best actually argument for a direct Urca process is SAXG 1808, which is not an isolated neutron star.
That's a transient, right?
Exactly, the soft X-ray transients, yeah. And so we're putting that together now with this is Saeed Roy, this new graduate student.
Yeah, well, if I may comment, at high densities, if you have extremely small amounts of hyperons, even very small amounts, then you can have direct Urca going. I mean, that's one of my favorite candidates, but I have not done my calculations for that. We did it long time ago, and I don't want to repeat it again because I will be saying the same thing again. So I leave it to Andrew to do it.
Yeah, I will try.
Only small amounts. It won't affect maximum masses. It won't affect radii. You know, just a little bit of like a pepper or something like that.
Okay, then maybe let me ask my other question to Tyler, which connects to what we discussed in the chat yesterday, or basically what Alex and Prakash discussed. And this is, so at very high densities, Tyler, you include information from the perturbative QCT, right? And basically this is, this tells you that also that the speed of sound is 1/3.
Mm-hmm.
But let's say you remove this perturbative QCT constraint. Do you know, or have you tried how to estimate or quantify how much the radius of neutron stars, or the equation of state for that matter, how much they change? So what's the impact of enforcing these constraints at these very, very high densities?
Yeah, this is not something we have done, so I can't directly answer it. I can point out that the PQCD constraint is a little bit more constraining than it looks, because we do the matching. It not only has to pass through the energy density and pressure range, but rather it actually has to thermodynamically match, which means it has to also happen at the correct density. So basically there's like a third matching parameter that doesn't appear, so it's a little bit more restrictive than it looks like it is. But I haven't done what you are asking, so I can't directly comment.
Well,
what's
to
the
follow up
okay,
on,
go ahead, Prakash.
yeah, to follow up on that, suppose you were to move it to 30 or 50 or even 60, would it matter?
You mean move the density?
Yeah, I mean 40 is not a number that is set in stone, correct?
No, definitely not.
I remember reading even from the Finnish group 70.
Yeah, so I think I would personally suspect it's pretty similar. Like, I think the main effect is that, like, that you're enforcing the Stefan-Boltzmann limit somehow, because there's a very particular place where that happens. Like, you can't be off by a factor of 100 or something from that. But so I would think that where you enforce the matching would not change things dramatically, but it's not. We'd have to do it to find out.
Sorry, in all cases, the center of the neutron star would not lie anywhere close to it, right?
Oh yes, definitely. They're something like less than 10.
Yeah.
In all cases.
Okay, last call for questions. Otherwise, I just want to say that tomorrow we also have a day dedicated to discussions. So we will have 3 discussions that are led by 2 experts, and we will address all the topics that were raised in all of the previous 2 plus this day. So in the first 3 days of this workshop. And so we can come back to certain topics. And if you have more questions that come up overnight when you think about things, we can ask them tomorrow. Otherwise, if there are no further questions, I would like to thank all the speakers of the day again, and I would like to thank you all for attending. Yeah, and hope to see you tomorrow morning. For me, morning, for you, evening. So thank you very much, and see you. Bye-bye.
Thank you.